So defining multiplicity, let's look at this example. So this here is the characteristic polynomial of a 6 by 6. You see that we can factor out a lambda to the fourth, and that leaves us with this binomial or trinomial that we could factor. So this lambda to the fourth is the same thing as saying lambda minus 0 to the fourth. And so what that means is the eigenvalue of 0 has multiplicity 4, because there's 4 of them. And the eigenvalue of 6 has multiplicity 1, and the eigenvalue of negative 2 has multiplicity 1. So that's multiplicity. All right, similarity. So if A is similar to B, that means if I put A inside here, then B is equal to P inverse AP. Okay, I could also rewrite this, let me just write it up here, because you know about, about matrix multiplication. If I wanted to solve for A, then I could take the time and multiply on the left by P. And this P times P inverse would give me 1, right? So I get PB equals AP. And if I want to solve for A, then I could multiply on the right by P inverse. So I get that A is equal to PB P inverse. There it is right there. So there's a relationship between A and B, but it starts off like this. So since we know this, right, just carrying this along, and I'm just going to play with this. Hey, I know, what if I just do a change of variables and let Q equal P inverse? So if I let Q equal P inverse, then this would be Q, right? And that would be Q. And then if I take the inverse of Q, that would give me P inverse inverse, and that's P. And that's what this is. So Q inverse would be P, so I could replace this P with Q inverse. So you can see, just by substitution, A and B similar. A and B are just similar to each other. We don't have to have go back and forth between them. So A and B similar, we can get this relationship between them. All right, so what's the big deal about similar? Well, two matrices can have the same eigenvalues and not be similar. So similar is very different, and similarity is not the same as row equivalent. And two matrices being similar is not the same as being diagonalizable. So it's a really unique relationship with this P and this P inverse. Okay, so let's make sure we know the definitions of the diagonalizable and similar. So if A is diagonalizable, you know that means A is equal to PD P inverse, right? That's that diagonal matrix in the middle with the eigenvalues on the diagonal. Okay, if B is similar to A, that means I have, and I'm just going to use different letters. I'm not going to use a P here because I got P's over here, right? So I'm going to use Q inverse BQ. All right, so what they want me to show is that B is also diagonalizable. So in my head, I'm thinking, okay, I want to get B is equal to like a PDP inverse thing, right? That's what I'm thinking. Okay, so let's just keep going with this. So I'm going to take, and I'm going to solve for B out of this, because that's what I'm trying to show is something about B, right? So if I multiply both sides by Q, I get QA equals B Q, and then if I multiply both sides by Q inverse, I get QA, Q inverse equals B. All right. So what am I trying to show again? I'm trying to show that B is diagonalizable. So I want to, hopefully it can be a different color here, so I hope you can see I want to substitute. So I want to get in order for B to be diagonalizable, I've got to get the D in the middle there, right? So to get the D in the middle there, how about if I replace A with this? So let me, I'm running out of room here. Okay, so I'm going to say, use colors here, Q and Q inverse, right? And then the A I'm going to replace with P, D, P inverse. And that's still all equal to B. Get rid of these silly things. Okay, so what am I trying to show again? Oh yeah, I want to find that B is equal to some matrix with the D in the middle and then that inverse of that same matrix. I think I have it. The D's in the middle. I need that, so that's a good thing, right? So I need to have a matrix, O, D, and times the inverse of the matrix. I know. How about if if I let, I don't know, let's just pick a different letter. How about if we let K equal QP? So if I let K equal QP, that would give me K, and then carry along the D. Oh, and what is K inverse? How do we know, what do we know that about inverses when we have them multiplied? Isn't that P inverse Q inverse? It is. So this is K inverse, and that's B. So what we've done, I would show that B is diagonalizable. Yes? Good.